Okay, so my name's Edward Haynes. So I've worked in the field of data now for over 20 years. And the type of work that I do is very much from designing, building databases, optimizing queries, building reports, developing data migrations, cleansing data, things like that. So in all the type of work that I've been doing, I've always asked myself, how can I approach this so that the solution is elegant, it's robust, and it's performant? It's always the type of paradigm or framework. And so through that course of many years, I have developed a set of techniques that manipulate the behaviour of SQL Server to promote performance outcomes. And this is what I'm going to talk about tonight in terms of what I call query shaping. Now, this presentation is going to be cut down. I'm going to be working through it quite quickly. I presented it initially in November last year in Seattle as part of the Past Data Community Summit. And the first presentation I ever did. Talk about jumping in. So I'm happy to answer a few questions along the way, but there will be time for QA at the end as well. So we'll just try and hit a balance. And so query shaping concepts, this is broken into three sections. The first will be a visual introduction to what I define or what I think about in terms of query shaping. The abstraction and the visualization is a way of giving us a framework of understanding. Right, query performance. I think of it in terms of two basic axes. There is workload and there is throughput. And you can look at these in terms of like a dial. So if you dial up workload by the red arrow, then at the same time you're going to dial down, generally speaking, throughput. And the idea here is that as you increase the workload and as you increase I/O, you're going to cause constraints, potentially bottlenecks, but essentially there is going to be a degree in which throughput can be constrained and the query takes longer to reach its conclusion. And the three factors that intersect all of this are memory, disk, and tempDB. So it's just a visual grounding, and I'm going to look at this in terms of, as you'll see throughout the presentation, I'm going to start having dials with red or green arrows on them. And it's just reinforcing this general concept. So moving on, when we build a query, it can generally, if you move into something that is more complicated, it's going to potentially make use of tempDB. And the idea here is that you've got intermediate stages of the query. It's going to develop a kind of a workings out, intermediate stages of data before it reaches its conclusion. Now, I'm trying to graphically represent this because in terms of the way the query works, you've got a database query, it's accessing the user database, and you want to get a result. As soon as you interact with the tempDB, you're going off in another direction. You're saying, well, I've got all this other work I need to do in tempDB, and you've got this other access happening, which introduces iterations, potentially within iterations. And I'm just trying to graphically reinforce that that can have a profound impact on performance. Hence, I'm showing one with the red arrows of workload throughput, and one with the green arrows. Quick question?
Yes, quick question for tempDB. So when you say improving performance, are we talking about memory and speed?
We are talking in terms of memory. SQL Server will, the way it's designed, it's a very clever database engine.
Yeah.
Whenever there is RAM available for the data load to move into for your queries and the tables that it's accessing, it will always, where possible, move that workload into RAM and give you significant performance gains.
Yep.
And the other thing is even portions, not necessarily all of it, but portions of tempDB can reside in RAM as well. Yep. So it's all about how busy SQL Server is, or Azure SQL is at the time, as to how much RAM is available, what your quota is, and what it can actually do. So you could have a quiet time, and everything's going into RAM really nicely. You could have a really busy time and suddenly your queries are running much more slowly because it's doing a lot more I/O. The TempDB and the tables that it's accessing are residing off the storage rather than getting cached in memory. But the principle here I'm trying to reinforce is that the more iterations, the more workload that you push into TempDB, you are increasing the workload. And as you increase the workload, and the key thing I'm trying to stress here is these are general principles. This is not a 1 + 1 = 2. This is a behavioral principle that generally applies. It won't necessarily apply in all situations. But generally speaking, as your query causes more TempDB work activities, it pushes up the number of iterations. It pushes up the potential for you to be generating I/O off storage, and there can be a dramatic slowdown in the behavior and performance of your query. But that's what I'm trying to get at.
Okay.
As an example, just to give you a bit of I suppose, an anchor in terms of where I'm coming from, I'm applying these techniques at work at the moment. The project I'm working on is in relation to a big migration. There's a team of us, and I'm focusing on the reporting side where we're moving SSRS. We're moving away from SSRS and we're moving to Power BI. We're also moving away from an old legacy Azure SQL MI instance. We're moving on to a whole nother enterprise framework. So the work that I'm doing at this moment in preparation for the migration is I'm taking the stored procedures that are called by SSRS and I'm optimizing them using this technique. At this point in time, because of the way I'm rewriting the code, which we'll get into, when you start generating a large number of records in these reports, so for example, 60,000 for one, over 100,000 for another, it can take easily about 45 minutes for the report to run. I've now got it down to about 15, 17 seconds. So in this particular case, the technique is providing dramatic results. It doesn't always provide us dramatic results, but where possible, these techniques work. So I have to be conscious of time and keep moving. So this is reinforcing it, but this is also talking about how, depending on the design and the workload, you could find that TempDB and the user database is all off disk, off I/O. Where possible, as I mentioned earlier, you could actually see your data in TempDB partially, to some degree, residing in RAM when the SQL Server engine has the capacity to do that. So the general idea here is that if you can do anything to reduce the workload, you are promoting SQL Server to have a greater opportunity to push its data that it needs into RAM. And that then can give you a greater potential for performance gains as well. It's just like a secondary benefit, but it can actually be profoundly enormous in terms of the performance gains you can get. In terms of query shaping, I can't really stay here for very long, but again, I'm trying to draw the visual paradigm here of what the idea of a query that has a larger workload and therefore it's got greater constraints with its throughput, as denoted in the red area. It is actually possible using techniques that I'm going to go into to recode that query and to promote a smaller workload and better throughput and to push it further up into RAM. So the difference here is that the red circle and the green circle actually relate to the one query that's then been rewritten to promote more performant outcomes. That's the general idea.
Is that always towards the disk? Like,
sorry?
If you go back to the previous diagram, anything that uses a lot of disk is generally slow. Anything that uses more
RAM is extremely fast. Magnitudes faster.
Yep.
Yeah. Exactly right, yes.
And that's what you're aiming towards in terms of shape.
Well, that's part of what I'm aiming for. It's about reducing logic iterations, where possible, reducing workload. And as you can do that, the benefits cascade out because you're reducing I/O. But further than that, as you do reduce its work effort and can actually reduce the volume of data that it's processing, you're then providing greater opportunity for that workload to be pushed up into RAM because it doesn't have to fit something this big into RAM. It can now fit something a bit smaller into RAM, and it becomes easier for it to do that, so to speak.
And would this pattern work in the case of cloud DBs as well, where you don't have much control over what's in the disk versus what's
Sorry, I didn't quite hear that.
like in Azure SQL, for example, the DB, you don't have control over what goes into the RAM versus what goes into disk.
Well, the performance optimization that I referred to with the SSRS reports, that's in relation to Azure SQL MI. And the behaviors that I'm talking about are tied explicitly to the SQL Server engine. So I can use these techniques on premise, on Azure SQL database, and on Azure SQL MI. And you'll see in the diagnostic tool that I get to fairly shortly, that's actually designed to work across all three engines. Yeah. So I won't hang around on this one for very long, but the idea is I'm just trying to break open the type of options that come out of this visualization, this abstraction process. So, for example, if you increase index coverage, then as you increase index coverage, you're providing greater opportunity to be more efficient in getting to the data that you want and thereby reduce I/O, thereby reduce workload and get a much more performant result. But this matrix is really about just exploring the type of impacts that you can have. I don't really have time to go into this now. So that's just reinforcing the visualization framework and the idea of there being design choices. And as you explore design choices, you can move from the left side to the right side. And finally, I've thrown this one in as well because the process where I'm dealing generally with SQL Server behaviors, there's a kind of an optimistic outlook that you can try a few different things. And the idea is that you make the query more efficient, you reduce the workload in TempDB, but you can also, I found, reach a point where as you push more and more things into memory, you can potentially hit memory pressure scenarios depending on how busy the SQL Server is as well. So while you've got this general framework that you're working towards, you always need to keep in mind memory pressure can then push back on the outcome. So you've got it as a counterweight to monitoring how effective performance tuning is. So I'm now going to get into a tool that I've developed. Now, this tool is a stored procedure, and it's taken me So it's taken me about 3 years to develop this tool in my spare time. And the challenge I made for myself was I want a tool that is, because I couldn't find one that did what I needed it to do. I understood query shaping enough to be able to use it, but I didn't have the ability to communicate it. And it's like, well, how do I communicate it? I need something that can give me tangible metrics that people can anchor to, that they can understand, oh, yes, you are actually making changes here. So I've effectively worked on building what I analogously call a more powerful microscope. This tool can be used for first response troubleshooting of queries that are in flight and give you a great deal of insight into what is happening in terms of the SQL Server engine and how it's processing queries. And the key thing here is because it gives you on-demand diagnostics, as you make performance optimization improvements to a query, you can then run it. And if you need to use a tool like this to give you feedback on whether it's actually giving you the performance gains that you're looking for. because some of this is a bit exploratory, and the techniques give you a general foundation, but then you just need to work through the permutation, shall we say. So I'm going to go through this really quickly. This is a very brief introduction, and the one thing that I haven't done yet is to write a user guide for this. I've been too busy. Okay, so it pulls data from 24 dynamic management views. It's very comprehensive. It starts by looking at in-flight requests and then looking at memory grants and schedulers and tasks, but it just keeps going and going into other areas like it can, I forget the name of the DMV, but it can give you insight into your in-flight query plan. And there's a DMV that gives you a range of key metrics about whether it's doing a scan, what the estimated scans are, and basically using that type of information, it will do things in the output. Like if you're running a delete and it's been running for an hour, it will actually give you an approximate percentage of how far through the delete it is. So it might be 80%. And it can do that with an update. You can do it with a number of commands, so long as they're not too complex. It'll detect if a command is complex, and then it will not provide a percentage estimate. If you're running a backup or running other DBCC commands and so forth, there's a whole range of things where it can give you an estimate on how far through that command is. Now, this is a general breakdown of all the types of information it can provide. It is something that we'll work through. I need to keep track of time. Let's see. The most interesting thing that this tool will bring out that is unusual with any other comparable tool is a column off on the top right-hand corner called performance indicator. And that actually can expand out with a heap of keywords and informationals that give you insight into what's happening at the time, whether there is a lock contention, whether the IO scheduler is getting banked up, or there's CPU contention, whether you're running a command like delete, and it can give you an idea of its percentage complete. Now, let me just move on, because we're going to come back to looking at specific elements here.
Just one question.
Yes.
So that is over what period? Is it 1 day or?
Oh,
Thank-
no, the general responsiveness of this is 1 or 2 seconds. So you just, and I've deliberately designed it so you do not enter any parameters. You just type in that command, exec sp_perf SQL, and typically in 1 or 2 seconds, it will give you all the output of in-flight queries. Sorry, I haven't spelled that out. It only looks at queries that are currently running. So it's not looking to do detailed monitoring and log analysis and anything like that. It's saying what queries are active on the system at the moment. And here's a breakdown that gives you as much insightful and useful information possible from a whole range of DMVs.
At that instant?
For that point in time, yes. Yes. Does that make sense? Yep. And if you flick against SQL Server Management Studio, if you flick across to the Messages tab, to help keep it separate, but it's just printed out, I've got a range of just general server-related statistics that say, here's the server memory, the non-database pages, UniFlight last spills, which is useful if your queries have in any way exhibited spills into TempDB. That's a useful point to confer with. CPU queue length, IO pending count, thread shortage. So things that can give you insight into whether the general SQL Server engine is exhibiting any kind of pressure, potentially. So I'm giving an example here of creating a clustered index. Performance indicator is saying, yes, we're running a create index command. It's approximately 54% finished. And I can do that because I've got information around the estimated scan rows, process scan, the estimated sort rows, process rows, and things like that that give me the ability to do that rough approximation.
So that makes it dependent upon your statistics being up to date.
This is
because the query plan will pick that up, obviously, as to what it's seeing, and
this is
working out the query plan.
This is I forget the name of the DMV. It's I can look it up afterwards, so I don't interfere with the slides. But there is a DMV that gives you in-flight statistics that.
Yes, so, it's the same one that does the live query view.
Yes. Yeah. So yes, if that live query view is skewed because it's not got access to up-to-date statistics, that could impact it.
Yep.
Yes. But it's effectively doing the same things like query view.
Sure.
Yeah. Okay, so the other things that I've got in here that I'm just quickly touching on is the idea of rank 1 TempDB, rank 1 memory grant. See, the other thing this does is it accesses the query store, and by doing that, it can start looking at the history of the query. So although it's focused on giving you a snapshot of what's happening here and now, where there is historical information that it can access and give additional context, it will try and do that as well where possible. And so the idea of a rank 1 and a rank last is for this query, if it's been run multiple times, what was the minimum amount of TempDB allocated to the query? What was the minimum memory grant? And associated with that minimum TempDB? And then what was the maximum TempDB associated with that query? And then in relation to that maximum TempDB, what was the memory grant size associated with that? And you can look for whether there's any signs of there being a fair amount of consistency between rank 1 and rank last. But if there's a huge variation, then you might want to ask yourself, well, are there severe swings in the workloads of SQL Server? Is there a potential for parameter sniffing, things like that? Things I can't really get into at the moment. This graph kind of really emphasizes that point. And the idea again is that, that with rank 1, where you've got a smaller or no TempDB allocation for that query run, you're promoting more efficient workload within RAM. And by doing that, your throughput, your performance is going to be noticeably more effective. If you have a lot of your workload sitting in TempDB, and this will come out in the next few slides, if you have more workload for that query residing in TempDB, then it's going to generally exhibit a less performant outcome. Now, the thing that I haven't really stressed here and that I've experienced time and again is I can take a query and I can rewrite it and I can push it from a significant amount of TempDB usage down to a minimal amount of TempDB usage. So that's what we'll get into soon. That's right. So with this tool, we've got some general threshold patterns like significance bin. I'll have a general threshold pattern of 5, 20, and 80%. So, for example, if you have missing, it'll work out a missing index percentage. If that's above 20%, then it will flag it in the performance indicator column as something that may be relevant. It's kind of setting up some thresholds to say, okay, well, we're going to, I want to hit a balance between meaningful metrics without you having to, whoever uses this, without you having to play around with parameters, which can only confuse the way it works. I just want it to sort of be as simple and as efficient to use as possible. In the way things like the thread scheduler and so on work, it will work on the idea of these categories for the query cost, which is an internal indicator. And it's not something that we want to expose, but in terms of identifying a category for the query, I'll look at the query cost and actually say whether it's low, medium, high, very high, which is consistent with something in SQL Server about the way it can schedule operate its own internal operations. That's all that's going on there. And so the idea then is if I want to do certain diagnostics around a query, I'll say, well, it needs to be a significant query. If the query cost is low, then it's not significant. I'm again just trying to set up some thresholds. So here's a range of things that can come up in the performance indicator column. So for example, alter index, alter table, create index, delete up to, select into, can all give you an approximate percentage complete. It will also look at database transaction units, and depending on certain thresholds, it can give you a guess, I suppose is the best way of putting it, saying you may be experiencing a bottleneck here because you've hit a tier limitation or there's just a certain amount of contention, so that you have an avenue of exploration, which is designed to be, I hope, more meaningful than just looking at, say, wait states or something like that. And again, I'm doing a similar thing on the IO. So this really depends on whether it's DTU or IO. Really depends, in this case, whether we're looking at the Azure environment or IO for on-premise. But it is able to detect what type of engine it's working with and maintain. There's only one version of this store proc. There's not one for on-premise and one for Azure. It's one piece of coding and it works on all platforms. So I won't hang around on here. Get into, there's just so much here. So what I've done is I've built a couple of rough data sets. And I did that by running these two queries. They're the same query, but I ran them at different times. And because there was a different set of operations and history and so forth within the SQL Server developer instance that I have on this Surface Pro, I got a different set of data and a different number of rows. But the examples that I'm going to show are based on these two data sets. Okay. So this is a simulation just to reinforce the type of outputs that you can get. So in this was me just playing around and deliberately creating problems for myself. But I just want to give you an idea of what type of display we're going to be looking at here. Performance indicator in this instance, we're showing contention in terms of disk I/O. Sort estimate was a bit low compared to what's been processed, which was far higher than the estimate. There is a range in because I've run it multiple times, so there's now a range in the runtime, and it's triggered a certain threshold that's saying, yes, it's got parameters, there's been a variation. So we're looking at memory pressure potential based on the way rank 1 TempDB and memory grant and rank last TempDB and memory grant are also behaving. It gets a little complicated, but it does use some clever logic to try and estimate if there is memory pressure potential without giving you a false positive. That's something for the documentation later. And once you reach a certain percentage of effort happening in TempDB, it'll just flag it as saying there's a certain 60 TempDB load. So you've got other things here. Oh yes, so underneath it, you've got the rank 1 mem and the rank last memory grant. And you can see there's huge variation, and it's giving you information around memory grants. You've got TempDB information here where it's saying, well, it's now allocated 945 meg, it's deallocated 229. So you can see the TempDB in use of 715. It's trying to give you an understanding of the work effort and trying to quantify what's going on at the SQL Server engine level as to the maximum extent I can possibly do using DMVs. So it's on demand. So section 3, final section. This is where we start talking about methods of coding. When I look at a query, I always break it down by understanding what joins I have, and then what filters, and then what sort operations, and then the result. And this is really key, because when you look at a query, when I observe a query as it's run by SQL Server, it's really important to say, well, do I have index coverage? Yes, that's an important question, but do I have index coverage from where the query optimizer is going to really essentially start engaging with your query? And that's going to be at the join. If you can have index covering at the join, that is going to provide significantly more performance gains for you than if you just have index coverage at the sort. Because it has to start with the join, it has to start working out how these tables relate to each other. And if it doesn't have index support, it's going to start doing table scans. And if it does the table scans, then you're really pushing up the workload as compared to having index coverage where it can do an index seek to find the exact rows that is required, thereby reducing I/O and increasing performance. So it's interesting when you start looking at a query that if you can understand that there is, generally speaking, because the query optimizer is very sophisticated and very clever in the way it's designed, but as a general principle, when we're talking about query behavior, I find it's very helpful to look at the join and ask yourself, if it's important to improve performance, ask yourself, does the join have index coverage? Once you've resolved that, does the filter have index coverage? After that, does the sort have index coverage? A group by is a sort. It's not. So when I talk about a group by, that is actually a sort operation, and distinct is a sort operation. It has to, because it's organizing how the data relates to other records, and it does that by effectively doing a type of a sort process. So what I can then say, okay, well, by breaking it down like that, I can then start thinking in terms of, well, if I can cover point 1 and then point 2 and then point 3 and then point 4, I have what I refer to as index reach. So I'm covering all those key facets of the query. And by doing that, I'm actually manipulating the engine to rely less on table scans, for example. I'm just trying to, I suppose, conceptualize this as much as possible. But by improving index reach, I'm reducing the workload and I can potentially significantly increase throughput. So let's go into this in a bit more detail. I'm bringing it back to some of those earlier diagrams. And what I'm pointing out here is that you've got an anchor at the join. So the anchor relates to where the index design begins. So your ideal index is going to focus on join columns, and then the filter, and then the sort. So when I show in this example an index definition that covers A and D for the first index and B and C for the second index, I'm just reinforcing index coverage that's focused on the join, then the filter, and then the sort. So if we go back to these temporary work data sets that I showed earlier, one was about 3.5, the other about 2.5 million records. If I run this query without any index support and I run spperf SQL, in this particular instance, it was telling me there is missing index potential at 39%, memory grant of 833, and a TDB allocation of 474. So what happens if I create an index? if I create a clustered index, the memory grant goes down to 12, which is a huge improvement, and there's no tempdb usage at all, at least. And I must stress, when I run SPPerf SQL, I'm carefully timing it so it's later in the run of the query. So there's been plenty of time for things to happen. So I might be like 70 or 80% into the query before it finishes. And then I run this to get the diagnostics to try and give you to display as some realistic metrics based on this example. If I create a unique index, interestingly, it's not as effective, which I don't entirely fully appreciate the differences, but I can understand the value of using clustered indexes. They have, however, a bit of an overhead, of course, because you're organizing the data according to the cluster, but what we have here is very different behavior. If I create a reduced memory scenario, so basically I go into SQL Server and I say you have 1 gig of RAM to run in, and I'm simulating basically memory pressure. Then the clustered index is still at tempdb 0. It's, in this particular instance, the memory grant is now null, which means it's probably still cached, possibly some results, but it doesn't need, it's just pulling the data directly via the indexes. It doesn't need to do any extra effort. So it's just streaming the data directly from the user database. In the case of the unique index, tempdb allocation has gone up, which is not surprising when you've got a memory pressure scenario. So join and filter. I'm just going to work through a few permutations here because it will start to make sense once I get to the end of this. If we now add a filter and there is no index support, interestingly, the average missing index percentage goes up, but the use of tempdb goes down. I said the query optimizer is a very sophisticated and clever beast. So interestingly, once we start filtering results, it's doing some clever work behind the scenes to reduce its reliance on tempdb. Now, if I create on this join and where scenario a clustered index or a unique index, tempdb is 0. In the case of the clustered index, it's just streaming the data from the database. In the case of a unique index, it is actually allocating a fairly sizable chunk of memory to run that query. That's just the way the query optimizer works. But it's very useful to know this. Again, reduced memory scenarios. So we're in a memory pressure situation. The clustered index is still holding, it's still behaving consistently. So there's no tempdb usage. It's just streaming the data. So there's no memory grant. Otherwise, with the unique index, it's pouring more effort into tempdb and memory grant is constrained compared to before. Now, join, filter, and sort. So building up a more complex query with the join followed by the filter, followed by the sort with no index. We're seeing a more sizable memory grant, and obviously a lot of activity is happening in tempdb. So let's compare this. With a clustered index, you'll see that in each of these examples, the index definition is expanding out further. So we've got coverage on ID, login time, session ID, and now total elapsed time. And you'll see that I'm carefully aligning the index definition with the breakdown of the query. So you've got section 1 here, section 2 at the where clause, and then section 3 at the order by. And so I'm carefully aligning the index to work with the columns that relate to section 1, then section 2, then section 3. And when I do that, it's writing that index very effectively. Now we're starting to see more effort going on because it's doing sort operation as well. So behind the scenes, it's not able to just stream the data. It now has to start sorting and doing iterations of processing in order to get the right the records out in the right order. So it's interesting though that because we have ideal index coverage, your TempDB is 0 megabytes, and it's just got a relatively hefty memory grant allocation to support that process. So what happens if we reduce memory? So we've got effectively memory pressure occurring. MDB suddenly shoots up. The memory grant obviously is reduced because it's not able to accommodate the ideal memory grant that it wanted initially. And let's just go effectively, because you're now working in TempDB, you've got this extra iteration of work taking place where it's got this relationship between your query and the user database that the query's drawing data from, but now it has to coordinate its efforts in the query plan to make use of TempDB. And TempDB, depending on whether you're pulling data off disk or whether that TempDB is residing in RAM, if it's disk I/O, it can be a huge slowdown for your query. And that all depends on what the scenario is. In this scenario, we've got reduced memory, so we're simulating memory pressure. So it would be reasonable to say in this scenario that TempDB is just going to be exhibiting, relying a lot on disk I/O. That is going to be a significant performance drag to the way this query works. Does that make sense? Yeah. Okay. And that's why I'm reinforcing it with the dials here with the red, because we're now increasing the workload effort and we're lowering throughput because there's this drag effect taking place. So what happens now if we start playing around with the index coverage? In this example, I've got, so now I think from memory, I'm just focusing on clustered indexes, generally speaking. And if we cause a break in the index definition, so we're covering the join, the ID and the login time, and then in the definition, we don't bother with the columns referenced in the filter, and we just cover the total elapsed time, which is the sort column, then we're finding, compared to before, where we had 0 TempDB usage with ideal index coverage, we've now got, because no memory pressure here, we're now finding that TempDB is shooting up to 712 meg, and it's just basically having to work harder to work through that because it doesn't have the ideal index coverage that's giving it the beta tree support to get to the records that it requires at stage 2 with filter. So it can use index support ideally for the join, but then it's having to work harder at the where clause because that filter is not supported by an index. So what I've done is, and I try to stay away from query plans. When I'm actually working, doing performance tuning myself, I very rarely look at query plans. And it's not to criticize them. They are an incredible wealth of forensic detail. It's just that the way I've trained myself to do this is I ask myself the question, if I look at this query and I understand it correctly, then what does its most optimal version look like? And I look at a query in terms of the SQL Server engine behaviors that it promotes. And you'll see it probably doesn't jump out as much in my examples because I've kept them fairly short, but you'll see that there's very careful indentation in the SQL code, and I do that with all my work, that indentation allows me to more easily see the join logic, the where logic, the sort logic, and whether that logic relates to a subquery or the primary query. And once I can easily see the join logic, where logic, and sort logic, I can then start to ask myself, well, do I have index coverage? Is there a better way of writing this code, et cetera, et cetera? But I can prioritize my effort knowing where I should start looking at the code first. So neat code is actually really conducive to writing performant code. So in the query plan, you have something called seek predicates, which is basically saying the query optimizer is using these columns to travel the beta tree to get, using the index to get to the exact records relevant to the query. And then once it gets past that point, it will use predicates to then basically do some additional filtering, generally speaking on non-key columns, but it's just additional filtering to get the final result. So you'll see that when we have a definition that has this, what I refer to as a break in coverage, the query optimizer is using ID and login time because it's got ideal coverage. But once we hit that break, the seek predicates show us that it's not actually using the total elapsed time for the sort because it doesn't have that continuity of index coverage to support it. So it's now using other techniques to get to the end result. General principle. So another example, what if we reverse the index range? So instead of saying, and just to show the query again, so we have a join on tables B1 and B2, and the columns that are relevant are ID and login time. And then at the end of the query in section 3, we're ordering by total elapsed time. So in this instance, I'm saying, okay, well, let's just show how messy this can get. So I've created clustered indexes that, or in this case, in a unique index, that completely reverse it around so that it starts with total elapsed time, and then it covers the columns used in the where clause, and then it covers the columns at the end of the index definition that support the join columns. And as you can see, it's I'm talking there, it's referencing an average missing index potential. There's a significant amount of work happening in TempDB. Without going into this, because time is brief, let's just go to here and we see that the seek predicate is CPU time. That's all it's using on data tree. And then it's going into filtering. So it's decided, the query optimizer in this scenario has decided that it will make reference to CPU time and which one was that one? B2, yeah. Because the index definition begins on B2 with CPU time. So that's the beginning of the index definition. So it's saying, okay, well, I can use that on the to help with the filtering, but that's basically it. And then it's all filtering after that. And so interestingly, when you have a composite index definition, the way you order columns can profoundly impact the performance of your query. So when you break it down and start to think in terms of your join, your where, and your sort, and how your indexes correlate with that paradigm, can have enormous ramifications for the way it all performs and hangs together. Does that kind of make sense to everyone? Yeah. Okay. SQL design patterns. That's where it gets even more interesting. Right. Trying to get back into a bit more visual space so we don't look at too much code. I find there's a very interesting behavioral difference between the use of or and logic. Now, they're very different. They work to isolate or filter records for very different purposes. But effectively, what I generally find is if you have a logic statement that uses or, you can think of it as creating multiple pathways. So for each or condition, it's going to explore this or condition, it's going to explore another or condition, it's going to explore another or condition, and it has to kind of work them out individually as you're processing all the data. It really expands on the iterations or the pathways that can be produced in a query plan. From my experience, it just generally increases workload. That's really what I'm trying to get at here. With an and, it's saying, well, you've got a single pathway, you've got logic condition and logic condition and logic condition, and so long as they're all true, that pathway succeeds. If any of those and conditions fail, the path stops, but you've got just one pathway, one logic pathway. So what does that tell us? Well, there are situations in which you can rewrite code to get rid of the or. So instead of having multiple pathways, you now have a single pathway. And I have used this technique on many occasions to improve performance. As the code gets more complicated, so that there is a greater amount of rewriting going on, you can shift it so that there is a greater computational overhead going on, and you reach diminishing returns, so you then no longer get a performance gain. But so long as the logic is fairly simple and basic, you can find that like a value equals 6 or a value equals 7, just say a value is in 6, 7. If you have, now like is terrible. If you ever see like, just replace it with char index. It is so much more efficient. But you can also do this. You can say, I've got C string is like something, or C string like else. And so instead I've got char index something plus char index else is greater than 0. It does the same thing, except it does it more efficiently. And when you start to get down to the last example where you've got a case when value 1 is null or value equals 0, then val 2 else val 1, you can start exploring the use of the null if command is null to basically filter it down to get the same behavior.
Very quick question.
Yes.
How much performance difference do you see?
Well, it does depend on your environment to some degree. So I would have to say that if you start pushing the workload into, say, using a bit more in, so this is last example, for example.
Yeah.
We've got a basic case statement. I'm pushing it into a functional paradigm. My take on it is that it's going to push a bit more into computational overhead. So if your server is, if you're doing some heavy lifting and your server's already computationally constrained, you may not find that there's any real gain.
Okay.
It's a bit of trial and error at times. I've actually created, in my example earlier about how I'm performance optimizing SSRS reports, I actually took a heap of user-defined functions because they're terribly unperformant, and I got rid of them. And I actually replaced them because they weren't particularly complicated. They were just doing a split string function and returning a set of rows and then looking for a value in those rows. I actually translated that function into a series of char index, substring, ltrim, rtrim, null if is null function combinations to do exactly this thing. And by rewriting the user-defined functions into this type of paradigm helped me achieve 45 minutes down to 15, 17 odd seconds. Doesn't always hold true, but if you are faced with a performance challenge, this opens up a door to explore and to see if it can help in your situation. If something is not a problem, don't fix it, you know. But if you're faced with a performance challenge, or if you want to get, or you're writing something fresh and building something new that needs to perform well, then here's some tricks you can, you know, pull out of the bag and just look at and see if it can help you achieve a better result. And so when the logic gets more convoluted, you just want to test the results and just see how you go. But if the logic's fairly basic, like in these first 3 lines here, it's, as far as I'm concerned, it's a no-brainer. It just works. It works really well. Any other questions?
Have you really seen anything with changing or to in?
Sorry?
Have you really seen anything where it's, you know, value is A or B, changing it to value in AB? Because that, my understanding was that's identical in the first level of simplification in the query plan.
Well, my experience, so what I'm relating here is things that I've tried over a significant portion of time, like over years. And as I apply these techniques, I actually see genuine results. So even though it's effectively meant to be doing the same thing, from a code level, all I can take from this is that the SQL Server engine is somehow treating it a bit differently, the in compared to the or. And it would make sense that if it hits an in construct, you can't necessarily say, well, what if you have an in construct with 10 entries? Then it can potentially, I don't know, but it could potentially in the engine work out an array and just sift through it and see if it exists. But the OR logic's going to be different. It's going to be creating, especially for more complex queries, it's going to be creating pathways to support each OR pathway to get to its end result. And it's not necessarily going to convert an into an OR when an OR is perhaps part of a bigger pathway, that type of thing. Does that make sense?
Not really in terms of how query plans generated. The first path would simplify those to exactly the same underlying construct. So I'd be surprised. I'd be interested to see your comparisons on just that one, because that shouldn't happen.
Well, yeah, I can certainly look into that and get back to you later.
Yeah, I'd be really keen to see that one.
Yeah,
because that's an interesting one, because it just changes my complete understanding of the way that the query optimizer is working on that first level of that first pass through and simplification.
Yeah, I mean, I've developed these techniques over quite a length of time, and I get results. So
cool.
If nothing's changed in the engine, perhaps I don't know, but I can certainly look into it and get back to you.
Yeah, that'd be brilliant to see some of that, because that's mind blowing if that's the case.
Yeah.
Excuse me, one question.
Yeah.
The clustered index, right?
Mm.
You have to wear some overhead, right? Because every time you insert a record, the index has to be.
It's sifting and sorting and organising that data according to the index design. So you do get an overhead. If you have a highly transactional table, a clustered index is not a good one. Because it could actually, the overhead of maintaining that cluster, that ordered sequence of data, could actually work against performance, even though the clustered index is supporting a performant query. And then that's why I'm showing clustered versus unique index design, because a unique doesn't do the sorting, but obviously it's giving some different results at times, but it's still a valid form to provide performance support. It just depends on how transactionally active and how big your table is as to you need to make a call on that.
Guru will look after everyone else and Kelly will wrap up. So
Yeah.
Just one other question. What about cached results? Very cache. Have you considered that in getting performant queries?
Insofar as when I work on a query design, I will, when I'm testing it, I will do a few things. I will primarily run it once, and that will promote where possible your table data and use it, the tempDB space and so on to move into cache. And then if I'm doing timings, once I've done that initial execution of the query, I will then look at running it a few more times. Depending on how busy SQL Server is, how much RAM is available, will impact on the way data is cached. It can vary over time. And so I don't examine cache so much as I look at for consistency in query behavior. And if you can help build a query that's supported by good indexing, then even if you have a SQL Server that's working harder and its workload is having to increase generally, that index support can provide more consistent behavior with the query, as opposed to, say, a scenario where you've got less performant coverage, and so your query might take a couple of minutes to run, and then at the middle of the day when things are really busy, suddenly it takes 20 minutes to run and you're scratching your head wondering why. It gets quite complicated. So in terms of caching, I think in terms of what can I do to promote an efficient execution of this query, because then SQL Server will work very hard to give me the best result possible. And I will rely on SQL Server to use its RAM that's available for caching purposes. But my job is to design the query to work as efficiently as possible, if that makes sense.
Yeah.
There's only so much I have control over.
Yeah, sure.
Yeah.
Sure. But if you ran the query a second time, it would have cached results, the same query.
Yes.
And so it'll run almost instantaneously. Very quick, very
Well,
quick.
it depends on the volume of data. And when I run the query, I haven't really focused on run times. I focused on the work effort that's going on behind the scenes and trying to highlight there are ways to reduce the tempDB load, and also highlighting that your index support is actually fairly contingent on how you align the columns, for example, with the query. And trying to reinforce that paradigm that when you look at a query, trying to simplify it to the point where you say, okay, well, what is the join criteria? And then what is the filter where clause criteria? And then after that, what is your sort criteria? And trying to work in that sequence when you're looking at index design. It has a profound impact on performance and consistency.
Sure.
Yeah. So if we now change from, before we were just looking at a filter or where clause with just and logic. So now that we've sort of opened up the presentation here to distinguish between or and logic, I will just have a quick look at that. Right, so this query is different to the ones that I've shown before because we now have multiple pathways in the filter logic in the where clause. I've created a cluster index that has ideal index coverage. And whereas before where we had just the AND logic, TempDB was 0. And memory grant was either 12 meg or was null. It was just streaming the results. So what this emphasizes that as soon as you switch to an OR design, you're now increasing the number of pathways, you're increasing the number of iterations. And so in TempDB, it's now going off and working out the results of all those iterations, of all those different pathway results. And if you were to go into the query plan, you'd see a different design for just an AND construct. You would see it having to work out different pathways. And again, I emphasize this is not the same query as before, but what this demonstrates that even with ideal index coverage, we're now looking at higher IO, or we're looking at a greater workload. So if I use these techniques to remove the OR construct, you can actually see that the query plan is behaving very differently. We're now getting 0 TempDB and a 12 meg memory grant. Same results, but instead of nearly 1 gig memory grant and 355 TempDB, by getting rid of OR, we're getting a very different behavior. Now, I must stress, because I'm using a number of functions here that can actually, you do reach a point of diminishing returns where it doesn't actually give you any real performance gain. So it's trial and error. But when your conversion to this type of paradigm is not too hefty, it's not too cumbersome, it can actually leverage significant results. So it's something in the toolkit when you need to refer to. The idea here is that your worst performance, when we start talking about an OR construct in join, where, sort, well, in this case, we're talking 1 and 2, so we're talking join and where. You potentially face the worst possible performance if you have an OR construct in the join, and you have your ideal performance where you've got index coverage 1 and 2 in circles here, but you've also got an AND logic if you are needing to do any sort of logic processing as well. So I'm just graphically representing that. And we build on that going back to the previous diagram by saying, well, in your design, we always look at the join, then we look at the filter, and then we look at the sort. And what we want to do ideally is move away where possible without getting too convoluted. But where possible, moving away from at least some of the OR logic constructs in the join and in the filter to promote a more performant outcome. So I'm going to go into an example. So now I have an OR construct in the inner join. This one was a challenge. I didn't run it through to the end. It was running for a couple of hours and figured it would probably take a few days to finish. I've given it ideal index coverage. And what you can see here is an estimation of the rows. So like the permutations that it's looking at must be absolutely enormous. But remembering that you've got one sample data set of about 3.5 million, other of about 2.5, and it's doing an OR across them. And TempDB is huge, 2.6 gig, and because it's just doing a simple permutational analysis, memory grant's not very big, but it's the permutations. And this is where the spool is giving us insight. There's enormous number of rows that it's going to produce to get through all the permutations that this OR construct in the join is generating. So question, question that I challenged myself with, and it took a few days to work through. Can I rewrite that query to get rid of the OR? The answer is yes. So I have effectively shifted the OR away from the join. I won't hang around here. But what I've done is I've created a union OR. And so I've broken it down. So I've got each of the conditions of the OR construct covered through the equivalence, and then one that is not equal, one that is equal for each side of the columns that are referenced in the join. That covers the same logic, but now TempDB is 0 megabytes. The spooling of permutational type work that it needs to do is significantly less. I forget the runtime, but it did actually finish. I don't need that comment there. The workload is drastically reduced. So there are ways of changing the query design to elicit more performant behavior from the SQL Server engine. It's an interesting relationship because the query is a construct that is enabled by the SQL Server engine. The query is something that it's a virtual construct that is sustained by the SQL Server engine, but the logic in the query is something that we breathe into the query, that we sort of create. But a query, and the thing that I've learned over the years, is a query can be rewritten into different versions to generate the same result. And as you work across different versions, you can get surprisingly different performance behaviors. And again, I'm also factoring in good index design as well.
So just to quickly confirm with the equals and the not equal signs that you see here using union, all that is practically doing the same functionality as an OR, then that's what you're describing.
Yes. That's covering the OR logic. Yes. And when I didn't do a select star, but I actually just did a select count.
Yeah.
For example, it's returning exactly the same number of rows as the original query. Count one. Just say, well, don't go into the leaf level. Just give me the number of records that you're processing. The logic is correct, and the rows returned is identical.
But
number of rows returned is identical.
Yet it's using a less temp deep.
Correct. Yeah. Because it has a different query plan. And it has a different query plan because the previous query isn't using this construct. It's using it's one query with an OR, and that's eliciting a different query design that's saying, well, okay, well, you've got one column or another column, two large tables, and it's working out a permutational matrix to get to the end result. And the query optimizer is doing its job. It's taking the query as you've created it, and it's designed a query plan that will work through all those permutations and get to an end result. In this instance, each of these queries is generating much fewer permutations to get to the end result because I'm breaking it down into subsets. It's just producing a more efficient outcome. And then when we move into subqueries, again, and I'm taking a bit of liberty with the graphics here, but it's basically, I'm combining the idea of as you promote good index coverage and reduce OR logic where possible, even when you jump into a subquery, which is then another iteration, that subquery starts the whole process again. And so each subquery can be treated as if it's got its own individual index support. So you could find that in your subquery, you're referencing a different index, but each query is typically, you should typically think of it like this. Each active query, each active table in the query can really be supported by one active index at a time. It doesn't make sense to have multiple indexes and expect multiple indexes to be sorting an active table in any one instance. The query optimizer will work out what index, if there's multiple ones to choose from, what index best supports that particular table in the query to promote the most efficient result. But when you jump into a subquery, you reset the process. So it may use the same index, or if there's another index available for that subquery, if it's the same table, it can do that as well. But the idea here is that through a combination of good index reach and minimal logic pathways, we're moving away from a heavy workload to a lighter workload. That's the general idea. So in the case of a filter with a subquery, if I take my initial my initial query with the AND construct, and I just happen to throw in this subquery here, then before we had temp DB of 0 megabytes. Now we see that there's a load in there of 74 megabytes, and that is, I think, safe to say, applicable here to the subquery. But if I then just add an extra index to support that by adding in a unique index here, then tempDB goes down to 0 megabytes. I'm more just emphasizing the impact on design and trying to show it as a tangible metric. It doesn't mean that you necessarily need to go to the nth degree with all this. It's just, there's a balance. You know, so like a query can run, say, in a minute. Is that sufficient for your business requirements? That's great. If you need a query to run in a matter of seconds and it's taking 30 seconds, then maybe you want to try and leverage a bit of extra efficiency gains, then, you know, it's your call. It's about providing choices when you need to expand your toolkit. So it gets a little more complex when you start looking at the order by. And so what I'm looking at here is if I take the query and I'm using the anchor point to emphasize, you've got starting point here with your join. You've got another anchor point here because you've got a subquery, which is a new query, and it resets the process of index coverage. So when we add the order by, what I was finding is I ran it a number of times, and sometimes tempDB would be 0, and sometimes tempDB would be 674 megabytes. And as you can see, the plan count, that there are 8 plans so far. So what's happening is the query plan, which is working always to ensure that it's delivering the most efficient result possible, is it's created a number of different plans, and it's making sure that as it works out different viable plan options, it's making sure that it's working towards the most efficient outcome possible. So I suspect, without having drilled into this further, that it's jumping across at least 2 different plans to make sure that it's maintaining the most efficient plan to render the results. So there's just a bit of fluctuation taking place there. It's not a big deal. So in a wrap up, there's a couple more slides to go here. I just want to emphasize the importance of looking the way I look at a query. So instead of having select up the top, I always look at it last. And so if you're looking at a query in terms of performance, select is the last thing you really want to look at. Start with the join, go to the filter, look at any subqueries along the way, and then look at sort before you look at select. And when it comes to designing that query structure, again, I'm just reinforcing the importance of considering how you write code. So with my select, I've got a nice even line here that says, okay, well, this is my primary query, and I can easily see the from, the join logic where it begins. I can see the filter logic where it begins and the sort. And rather having everything spread around the place, I've got a nice even margin, so I can quickly and easily see here's where my initial investigation of this query design needs to take place. If it wasn't written like this, I would have to put more effort into interpreting it to find, is that the correct primary join? Because we're talking only short queries here. As soon as they get bigger and longer and it's not indented, it can become quite a challenge to say, well, where do I start? So if I'm presented with a poorly performing query, and this has happened a number of times, it's typically very messy code. So I might spend literally a couple of hours rewriting it into this format, just tidying it up. And that's actually a better use of my time, because I can then quickly jump in and say, okay, well, here's the join logic, here's the filter logic, these parts line up. So this is my outer query, here's my subquery, and work through the process of making sure that I've done the code refactoring and the index coverage without missing a beat. And for those interested, if you would like to download and explore the use of SPPerf SQL, it's available on a very basic website at the moment, because I haven't done documentation, but www.queryshaping.com. Thank you. Any questions? Martin's gone. Have you got access to chat, Kelly? Right. Okay.
I have one question.
We
Is
have one
this just for Microsoft SQL Server, or
This just relates to Microsoft SQL Server.
so you wouldn't know whether the performance difference would come from, let's say, a MySQL or a Postgres SQL Server, or would the same principles, or would you be able to apply the same principles with trial and error?
I would guess you could apply these principles to some measure of success.
Okay.
I think because I've stepped back and I'm trying to look at behaviors in terms of minimizing logic and efficient logic pathways, efficient index design, I think to a point would translate to other database engines.
Okay.
When we're talking about traditional relational database engines.
Yep.
But it's not something that I've actually had a hand on. So I wouldn't be able to quantify that.
I see. But would the same OR logic permutating to other, how to say, within the table, would that same problem be within a different database server, or is it just unique to Microsoft's SQL Server?
I could only guess.
Okay.
And my guess is that to a point it would translate.
Okay.
But it's only a guess.
Okay.
But fundamentally, you are creating multiple pathways compared to an AND.
Okay.
Yeah.
Thank you.
One question, can you confirm the tempdb, isn't it? I thought it was non-RAM, it was on disk, right? Tempdb always.
Well, it's a really good point. Historically, I've thought of tempdb as being on disk. But when you actually analyze what SQL Server is doing and look at the segments that relate to tempdb, some of those will actually be pushed into RAM, into cache, if there's room.
Yeah,
So
if there's room.
if there's room.
Yeah.
But SQL Server will always prioritize. It has its methods for prioritizing what data is cached, what data is pushed into RAM, and I think it will be. I suspect, I can't qualify this, but I suspect that with any tempdb data that sits in RAM, it's tempered. It will always give some prioritization to user data that relates to a query. But I've never really explored how that algorithm works. I just know that you can find portions of
Right.
tempdb in RAM.
That happens.
Yeah, which is a good thing. It's an efficiency gain.
Hmm.
Yeah.